back to the Advanced Microcontroller series. In today's session, let us discuss about microcontroller interfaces with ADC. And here is the agenda: introduction, types, terminologies. So what do you mean by ADC? Analog to digital converter is nothing but ADC. A functional block which helps us to transfer analog signal to digital signal. So that is nothing but ADC. So this ADC block could be connected externally on board along with the microcontroller, or it could be built in the microcontroller. So what are the types of ADC? Flash ADC, pipeline, SAR, dual scope, sigma delta. So most common ADC used in microcontroller is SAR. What do you mean by SAR? Successive approximation register. And one more is the sigma delta. So this SAR, successive approximation register, is used in data acquisition, and this sigma delta is used in audio or video control application. In ADC, some good amount of terminologies are there. So what are they? Sampling is there, and resolution, bandwidth, channel. So we have so many. So it having big number of terminologies, but in today's session let us concentrate on few of important terms or terminologies which will useful while programming ADC. So first one is the resolution. So before that, what is ADC? Analog to digital converter. So whatever analog value translated into digital value, it will be stored into the ADC register. So the width of that ADC register is nothing but the resolution. So usually we have 8-bit resolution. So 8-bit ADC. So here 8-bit ADC have a bit from 0 to 255, and 10-bit having a bit from 0 to 1023, and 12-bit ADC have a bit from 0 to 4095. So total bit is how much in the 8-bit ADC? 266, isn't it? 0 to 255, that's why it is 260, sorry, not 266, it is 256. So this is about the resolution. And next is the full scale range, FSR. So what do you mean by full scale range? It is nothing but maximum amplitude of analog voltage that ADC can represent is nothing but FSR. So in the diagram, so here we having full scale range. What do you mean by full scale range? So it is the maximum amplitude of analog voltage. So that is nothing but the full scale range, maximum representable amplitude. And next is the step size. So what do you mean by step size? So ADC started converting analog value into digital value. So the amount of change in signal magnitude due to which value in ADC register changes at least by 1, that is called step size. So what is the minimum change resolved is there na, that is what called step size. So whatever analog value translated, it will be stored into the ADC register. So what minimum value it can translate, for which value it can resolve that change. So that minimum change resolve is nothing but the step size. So in simple terms, we can say that minimum value that ADC can translate, so that value is nothing but the step size. We can also call, sometimes we can also call step size as LSB. And this is the formula to find the step size: input range divided by 2 to the power of resolution. So here you can see the step size. So this is the analog input and this is the digital output. So here you can see the step size. And next is the channel. So channel is nothing but the microcontroller pin which should link external component to the ADC block. So we can say that channel is nothing but the pin, microcontroller pin. So here we having different sensor, light sensor, temperature sensor we having, smoke sensor we having. So all these sensors are connected to where? ADC. All these sensors are connected to ADC, isn't it? So, or external component also. Not only these sensors, we can connect external component also. And so here you can see via this pin, what happened here? So via this pin we connected ADC, isn't it? So these pins are called as a channel. So in digital signal we saying these pins as a port, but we are dealing analog signal now, right? So when we are dealing analog signal, it is not referred as a port pin. Instead of that, it is called as a channel. Here you can see for the ADC block only one channel is active and at one instant of time. You can switch the block to another channel also. You can switch it to this channel also. When you switch, once you completed the processing of current channel. So for example, this channel is active, which connects to the light sensor. You can switch to the another one once processing of this channel done. So this is about the channel. And next is the acquisition time. So once channel is selected, so let's assume this is a ADC block. So once channel is selected, now the selected channel number is which one? 3. 1, 2, 3, isn't it? So it is connected to where? Smoke sensor. So once channel is selected, we need to make sure we provide enough time to ADC block so that ADC block sample the signal at that particular pin. So that enough time is there, right? So that ADC block sample or understand whatever signal is there at that time, and this amount of time which we need to provide, that is nothing but the acquisition time. So it is also referred as the sampling time. So this time is differ from different ADC, not same. So this is about the acquisition time. So before doing the conversion, whatever time we are providing sample the signal is nothing but the sampling time. So what is the conversion time? So once signal is sampled, what happen? Conversion will start. So once conversion is started, again we need to provide the enough time to ADC, isn't it? So again we need to provide the enough time to ADC to translate sampled signal. So that is nothing but the conversion time. Basically in simple term, what we have to do, once signal is sampled by the ADC, it will start converting that analog signal to the digital signal. Still it is doing conversion. So analog to digital value. So we have given enough time, isn't it? So that enough time is nothing but the conversion time. So conversion time is the time taken by an ADC to convert an analog input voltage into a digital output value. So these are the common terms, few common terms, terminologies. Okay, these are the few terminologies. So in PIC microcontroller, we have few components which needs ADC block. So one of them is nothing but the potentiometer. So this is the PICSimLab. So here we having two potentiometer. One is pot 1, this one, and one more is this one, pot 2. So we having two potentiometer. So let's find out to which channel these two potentiometers are connected. To get that, what we need to do, we need to know the physical connection. So to know the physical connection, what we have to do, we have to use the schematic diagram, isn't it? So we have to use the schematic diagram. So where we get the schematic diagram, go to the PICSimLab Simulator, click board and then click the schematic diagram. Now where we having this diagram? So yeah, so here we having the diagram, isn't it? So you can see it is connected to analog channel 0. So let me highlight this analog, this is the highlighter, right? So yeah, let me erase this and use highlighter. So this is what? Analog 0 and this is analog 1. So you can see it is connected to analog channel 0 and analog channel 1, and port 1 is connected to the analog channel 0 and port 2 is connected to the analog channel 1. So how potentiometer is working? So as you varying the knob register is getting varied. So that's why it is called variable resistor, right? So as you varying the knob, resistor is getting varied and accordingly voltage is also getting varied. So let me open the PIC16F877A datasheet. So It's opening. So here, where is the ADC? Analog to digital converter. Click on it. So yeah, we get this, right? So the analog to digital converter module has 5 inputs for the 28 pin devices and 8 for the 40 or 44 pin devices. So our PICSimLab, our microcontroller, PIC microcontroller is 40 pin device, right? So here we having 8 inputs. So you can connect 8 different sensors here, but one can be active at a time. So now what is the solution if you have 10 bit? 10 bit means 0 to 1023, right? So before that, let me consider pot 1 pot. So yeah, so let me consider pot 1. So this is potentiometer which is going to vary the voltage, that is 0 to 5 volt. 0 to 5 volt. So what microcontroller will do if voltage, whatever pot is varying, if that voltage is greater than or equals to 25, then the so now we having one plan, okay? So if the voltage is greater than or equals to 2.5, then the microcontroller will turn on LED 1. So if the voltage is less than 2.5 volt, then microcontroller will turn off the LED 1. So this is our plan. So for potentiometer 1, so if voltage is greater than or equals to 25, then what is our aim? Our LED 1 is turn on. So if this voltage is less than 25, sorry, not 25, it is 2.5 volt, then what is our aim? LED 1 is turn off in that case. So this potentiometer is dealing with analog signal, but microcontroller is working on digital signal, right? So potentiometer output is analog and microcontroller work on digital. So to this voltage, so whatever voltage is there, right? So this one. So to convert this, so let me say with an example. So here we having pot. This signal is analog, and here we having microcontroller. This signal is digital. So what we need in between? We need one converter, ADC we need, isn't it? So the input of ADC analog and output is digital. So here we getting analog signal and here output is digital. So whatever this signal, the digital signal is there, converted digital signal, So where this digital signal is stored? So it is stored into the ADC register, isn't it? So here we having analog signal. So here what we having? ADC we having analog to digital converter. Then whatever output data is there, that is what? Digital. So analog is what? 0 to 5 volt, right? So analog signal we having 0 to 5 volt, and it is stored where? ADC register. So how long is the ADC register? That is 10 bit. That means 10 bit means ranges from 0 to 1023. So now analog voltage is 0 volt. So here we having here this is my analog. So this is what? Analog. This is for analog and this is for digital. Now analog voltage is 0 volt, means that is what? 0. Now next is the 5 volt. We are considering 0 to 5 volt, assume. So now what will be the maximum converted voltage? That is 1023, right? For 5 volt, 5 bit, we having 1023. So how to get this 1023? 2 to the power, we are using 10 bit, right? So this is the 10 bit register. So how to find 2 to the power 10 minus 1 for 10 bit? This one we discussed, right? So that is how much? 1023. So 5 volt means what? When it is 5 volt, then that is 1023. So now what is the mid voltage? That is 2.5 volt. So that means what? 1023 divided by 2 is 512. So now what my question is, now can we change the above? So instead of writing like this, voltage is greater than 2.5 volt for analog, so for digital, right? So yeah, for digital, can we write instead of 2.5, can we write 512? And in place of voltage, so 10 bit is what? It is the bit of ADC register, right? So that is what? ADC register. So all this converted data is stored where? That we already discussed, that is stored into the ADC register. So that is what? 10 bit. So instead of writing voltage, can we write ADC reg value? So we can write ADC reg value. And here also can we write the same? Here also can we write the same? ADC reg instead of voltage, can we write? Yes, we can write. And instead of 2.5 volt, I am going to write 512. So here also I am going to write the same. This is what? Digital value. So what we had for analog, that is this one. So the same thing we had for analog, that is what, 0 to 5 volt. But for digital we using like this. But usually for particular analog voltage, how to find the value? So if I want to find for 1 volt, so how to find? So for that we having one formula. So ADC range means ADC register range. So we having one formula. So let me write the formula. V divided by step size. But do you know what is step size? What do you mean by step size? We know step size is equals to input range divided by 2 to the power of resolution. So this is the power symbol, 2 to the power of resolution. So this is nothing but step size. Now resolution is 10 volt. Now we need to find the step size. So, but how to find the input range? Input range equals to maximum voltage minus minimum voltage. So what is the voltage range? 0 to 5 volt. Maximum is 5 minus 0. That is how much? 5 into 2 to the power 10. So how much is 2 to the power 10? So we know, right? 2 to the power 10 is how much? 2. We need to so instead of that we need to multiply 10 times. So no need, we know the value of 2 to the power 10, right, which is nothing but what? This one, 1024. So 2 to the power 10 is how much? 1024. So now 5 divided by 1024 is how much? This much, 0.004882813 volt. So yeah, 5 into 2 to the 1024, which is equals to 0.00488 volt. So this is the step size. Now we need to find ADC reg value. So how to find this? So let me copy this formula and let me paste it here after the step size. Now we need to substitute, right? So what is the voltage? So V equals to how much? 2.5. That is divided by step size. Step size is how much? 0.00488. So what is the value of this? This is nothing but 512.29. So we can write it as 512. Let me take only the integer value, 512. This is for 2.5. See here, for 2.5, 512. You got the same answer, right? So if I write 2 and divide by this, how much I will get? how much I will get? Check using the division method. So 0.0048. Now we got the value of 2 ADC range when voltage is equals to 2. So how much is threshold voltage of LED? It's around 2 volt or 2.5 volt, isn't it? So okay, let's discuss using the code. Let me open the code. So open MPLAB XIDE and open the code. So here we having the data sheet, right? So here you can see the ADC, analog to digital. Okay, it's opened. So this module has 4 registers, and these 4 registers are register ADRESH. So what it means? And it also so it's having 2 result register and 2 control register. So what are the 2 result register? So ADRESH and ADRESL, and control register are ADCON 0 and ADCON 1. So analog to digital, so result high register and result low register, and control register, so 0 and control register 1, ADCON 0 and ADCON 1. So our microcontroller is 8-bit. So whatever register we having, max bit of those register is 8-bit. To store 10-bit result, at least how many registers do we need? 2 registers, right? Because one is 8-bit. So here analog to digital result high register. So here we having total 4 register. So we have to configure these control register. So these control register and converted result stored into this result register. Okay, we have to stored into this result register. So okay, let me open the code. So here we using how many peripherals? 2 peripherals. So we have to do the initialization. So here we having macros. So LED 1 is connected to RD0 port D, and data direction register is TRISC-D. On means 1, off means 0. And here, so init config control will go to here. LED array 1 initially we considered as off, and LED array DDR 0 means LED is output device. Then control will go to the ADC code here. So what you have to initialize? Control registers, right? So whenever you considering any register, so how long is this register? 8 bit long. So bit 0 is the LSB bit and bit 7 is the MSB bit, isn't it? So here you can see, here we having 8 bit. So this is the bit 0 is the LSB bit, bit 7 is the MSB bit. And here you can see RW, what it means, readable and writable. And here we having U, what it means, that is unimplemented bit. So here we having bit 6 to bit 7. Here we having the last 2 bits are set to what? So this bit 7 and bit 6, these are the last 2 bits, right? These are set to conversion frequency. So conversion time of ADC depends on conversion frequency. So in this case we are dealing with simple peripheral, that is potentiometer. To set the clock frequency, 3 bits are there. So 2 bits from ADCON 0, which is nothing but ADC S1 and ADC S0, and 1 bit from ADCON 1, that is ADC S2. So since we are using simple peripheral, that is potentiometer, right? So we are going with the simple clock conversion frequency or default frequency. So this 0 indicates what? Default value. So 0 0, you can use default value 0 0. For next 3 bits, means bit number 5 to bit number 3. So these 3 bits are the analog channel select bits. So where the port 1 is connected, so it is connected to channel number 0. Then the 3 bits are nothing but 0 0 0. But what is the default value having these 3 bits? That is 0 0 0, isn't it? So is there any need to overwrite? No, right? Because it is already 0. And next is the go or not done bit. So here you can see bit number 2. So go or not done bit is nothing but start conversion. So as of now we are not using this. So when we are going to use after starting the conversion, right? So this we use after start conversion. So let's go with next bit. Bit number 1 is unimplemented bit. So before that go or not done bit. So here you can see when it is equals to 1. So in that time analog to digital conversion in progress. If it is equals to 0, that is not in progress. So this is about ADCON 0 register. Okay, let's see this bit later. So before that let's configure the bit, this one, bit number 1. This is an unimplemented bit, so no need to worry about this bit. And next is the bit number 0. So here you can see. So what bit number 0 is saying? When add on. So when add on bit is equals to 1, analog to digital converter module is powered up. And when it is equals to 0, so analog to digital converter module is shut off and consumes no operating current. So this is about the bit number 0. So this is about ATCON 0 register. And next we having another one register, that is ATCON 1. So let's configure the bits. So here also we having 8 bits. So let's configure the bit 0 to bit 3. So here you can see analog to digital port configuration control bits. So when you are using ADC, all these analog channels you have to set as an analog. So here you can see we have to set all the analog channels as analog. So by default we are using AN0. So by default we are using AN0 channel, and make sure this channel is analog. But so here we use it this one, right? 0 0 0 means it is what? AN0. But initially we talk about this bit, right? Read bit, readable, writable, RW. So here in the ATCON 0 register, so these are 0. Here you can see that is equals to 0. So by default all channels are analog. So let's not to pick that, keep it as a default. So here we using 0 0 0 0. And next 2 bits are unimplemented, right? Bit number 5 and bit number 4. So that reads as 0. And bit number 6. For the selection of clock conversion frequency, 3 bits are there. So 2 bits are from ATCON 0 and 1 bit is from ATCON 1. So that is what? ADCS2. ADC clock conversion 2 bits. So here you can see 2 bits. So this is also keep 0. We can go with the default bit pin. So here you can see we are going to use 0 0. And next pin is bit number 7. So ADFM, analog to digital result format select bit. So here this bit will tell in which format ADC conversion result is stored. So if this bit equals to 1, the write justified. So if it is equals to 0, then it is left justified. So assume we have a 10-bit result. So let us assume we have a 10-bit result. So that is what? Y, X, 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 then X, 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 X. So total we have 10 bit. So this is what? This is the MSB bit. And this one what? This is the LSB bit. So if ADFM equals to 0, then it is what? Write justified. So in the data sheet they mention if ADFM equals to 0, then it is write justified. So if it is equals to 1, then it is write justified. If it is equals to 0, then it is left justified. Okay. So we have to register for storage of result. So one is nothing but result high and other one is nothing but result low. So in case of write justification, out of 10 bit, 8 LSB bits goes to where? Result low register. So we have to know in the 10 bit. So before that, let's see about what is right justified and what is left justified. Okay, so let's see about the right justified and left justified. So where it is there, scroll up and see. So let's scroll down and see about right justified and left justified. So here you can see right justified and left justified. So now in case of right justification, so out of 10 bits we having, right? So out of 10 bits, so 8 LSB bit goes to the result low register. So 8 LSB bits go to the result low register. So means here we having 10 bit, right? These are the 8 LSB bits go to the result low register, and upper 2 MSB bit goes to the result high register where at the 0th and 1st bit. So here we having 0th and 1st bit is there, right? So other 2 MSB bits goes here. So these 2 MSB bits go to the 0th and 1st position, and 6 bit treated as 0. So out of 8 bit result, out of 10 bit, 8 LSB bit goes to the result low register and 2 MSB bit goes to the result high register where at the 0th and 1st position, and remaining 6 bit treated as 0. So this is what right justification. So if ADFM is equals to 0, then it is left justification. And here out of 10 bit, the same thing here I written. So here you can see in the right justification out of 10 bits, the LSB bits, right? So so this is what LSB. So 8 LSB bit goes to the AD, so result low register, and 2 bit goes to the result high register at 0th and 1st position, and remaining are 0. In case of left justification, out of 10 bit, 8 MSB bit goes to the result high register and 2 LSB bit goes to the result low register. At which position? Here you can see in the data sheet we mentioned, right? So okay, that we'll see later. Before that, that is go to the 7th and 6th position, and remaining we considered as 0. Here you can see remaining we considered or treated as 0. So in our code we are using right justification. That's why ADFM is equals to 1. And here you can see why add-on is equals to 1. This one we already discussed, right? Add-on equals to 1 means that is power on. So power on is equals to, so when you power on, you need to write add-on is equals to 1, and when you power off, you need to write add-on is equals to 0. So that is this one, right? Yeah. So once you setting this bit, initialization is done. Now come to the main function. So here it is the main function. So now while of 1 ADC reg value equals to read ADC. So whatever converted result is there, we storing into the variable ADC register value. So what is the maximum value? So what is the maximum value? 10 bit, right? So 1023. So when vary the knob of potentiometer, the voltage varies. The microcontroller read that voltage. So it is an analog voltage. So we are having ADC block unit. So whatever voltage varied ADC block converts into digital value. And let's read that value using the read ADC function. So let me go to the data sheet again. So here, here you can see in the bit 2 we are using go or not done function. So ADC conversion status bit it is. So if this bit is equals to 0, conversion not in progress, and if this bit is equals to 1, conversion is in progress. So the same thing we using here. Go equals to 1. Start the ADC conversion. So while of not n of done means not done. So here you can see this value. So once conversion is started, before reading the converted value, whatever converted digital value is that is stored in here, result bit, right? So AD RESH and AD RESL. So analog to digital result high register bit, and one more is result low. So before reading this value, we have to wait till the conversion is completed. So we are give enough time till ADC is complete conversion, right? So that which is automatically cleared by the hardware. So that is what while of go. So that is automatically cleared by the hardware. So when analog to digital conversion is complete, so when analog input is converted into digital, so while loop come out of the loop, isn't it? So here in the code you can see. So when in this condition, what happened in this condition? So we have to give enough time till ADC is complete conversion, right? So while of go or not done. So this is automatically cleared by the hardware. So when analog to digital conversion, so analog to digital convert is done. So when in that time the loop will come out of, so the while loop will come out of the loop. So this condition, not while loop, so this condition, so this one will come out of the loop when go is equals to 0. So while of go or while of not done, you can see now value converted and it is stored in this register. Which one? Analog to digital conversion, result high register and result low register, right? So what result format we store? So ADFM is equals to 1. What it means? Right justified. And we have a result low register and result high register. So result low register we have to store 8 bits. So this one we already discussed. So in the result low register, so we have to store 8 bit. So here you can see, and another 2 bit we are storing in the result low register. So now let's assume 10 bit value is so here we assuming 10 bit value equals to y, x, 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 x and x, 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 x. So ADFM is equals to 1 means what? Right justified. So out of this 10 bit, 8 bit value stores here and 2 bit value stores here. So ADRE SL, so here you can see the 8 bits. So let us assume my 10 bits are 1 0, then 0 0 1 0, then 1 0 1 1. So now in place of this, so here we having 8 bits. So this is 4 bits and these 4. Total we having 8 no. So these 8 bits are stored in result low register and remaining 2 bits are stored in result high register at 0th and 1st position. So let's take one variable, that is ADC reg value. So this is one variable. So now that is equals to ADRESL means result ADRESL result low register. So is this right? No. So this one here you can see, here we having only the 8 bits, not 10 bits. So for that we are using one OR operator. So here I am going to use OR operator. So how to write OR operator? Result high register. So can I write like this? So can I write like this? Now 0 0 1 0, then 1 0 1 1 and 0 0 1 0 1 0, sorry, first 6 bits are 0, right? 1 2 3 4 5 6 0 0 0 0 1 0. Now here we using OR operation. So what is the result of this? The result is 0 0 1 0 1 0 1 1. But what is R value? So here you can see R value is different one, right? So here compare 0 0. So here you can see 1 0 1 1, that is same. So this much values are same. But our value is not same, complete not same. So for this reason, I am going to use the shift operator. So here I am going to use the left shift operator. So now what will happen? So here I am going to write, here I am not going to write directly, instead of that I am going to use the shift operation. So now if we do this OR operation, what value you will get? So here you can see 1 0 1 1 0 1 0 0 0 1 0 1 0 0 0 1 0 1 0 0 0 0 0 0, and here you will get 1 0, here you will get 0, and here you will get 1. The same value you got now, right? So the value is same now. So why here we used shift operator. So after the while of not done, so here you can see after the while of not done, we using the same line, right? Same line we are using. So what result is there that is returning here? So now here you can see ADC reg value equals to read ADC function. So here converted, so what happened here, ADC value, reg value equals to read ADC. So reading the converted value from ADC and converted into that variable and to glow the LED coding this function. So here you can see glow LED of ADC reg value. So here you can see the glow function. So the same thing we discussed, right? So if ADC reg value is greater than or equals to 512, LED on, else LED off. The same thing here we discussed. So here you can see when it is greater than or equals to 500, LED glow. When it is less than, LED stop glow. So this is about the code. Let's build. So here we having build option. So production, clean and build. Go to the PICSimLab Simulator file, then load hex file. So here which one? ADC sources, single channel detection, distributive, default, production, and this. Yeah. So vary the pot. Slowly vary the pot. So before that here port D we are using. So vary the pot and see. So when value is greater than or equals to 512, LED glow, otherwise LED not glow. So this is about the code. So single channel detection. In the next session, let's see about the multi-channel detection. That's all about today. Thank you all.